Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at the product of two series and as to what happens to convergence of the product, and first of all what is the definition of the product of two series, etc. Last time we discussed absolute convergence, which is to say that suppose I am given a series, we say that this is absolutely convergent if this is a convergent series. So that's the definition of an absolute convergent series, and we saw that, amongst other things, we saw that the absolute convergence of a series is insensitive to rearrangement, meaning if we take a bijection sigma and we have some absolutely convergent series, then first of all the rearranged series also converges absolutely at that, and in fact they have the same sum. So this is what we saw. These are the problems. And now let us get to the material of this lecture. Before we define what is the product of two series and prove the relevant theorem, let us look at a technical looking lemma. This will not make sense as to what is the motivation behind it, but let's just get this out of the way first. So we are given an absolutely convergent series. In fact, I think we don't even need absolute convergence. Let's see if we need absolute convergence. I think just convergence should be enough, but anyway. And suppose we have some sequence of numbers such that they converge to 0. Alright. So then define this weird looking number gamma n as this expression. The 0th guy. So it starts with 0. I should mention that. So this thing is actually 0 to infinity. So this indexing starts from 0 rather than 1. So this is the 0th guy hit with the nth guy in the series, in the sequence, and so on. So we just add all of them, and this we report as gamma n. And the conclusion is that gamma n converges to 0. So this is what we want to prove, and this is a weird looking lemma, but this will be important. So let's prove it. In fact, this is a good exercise, so you can pause the video and take this as an exercise also. Okay. So let a equals this number. So yeah, we are using absolute convergence, I think. Maybe let's see if we can. Yeah, I don't think I can avoid absolute convergence. Let's see. So we have this number. By absolute convergence, this is in fact a real number. This is not infinite. Okay. And we may assume that this is greater than 0. Because if this were 0, then each an would be 0, and then this would be trivial. So this would be, each gamma n would be 0, and then this is trivially true. So we may assume that this is greater than 0. Okay, so now let epsilon greater than 0, and we want to show that that this thing is less than epsilon ultimately. This is what it means to say that this converges to 0. Okay, so let n greater than equal to 1 be such that whenever little n exceeds capital N, we have this inequality, and this makes sense because Bn converges to 0. So since Bn converges to 0, there is indeed one such capital N such that this happens. Okay. So then, if little n exceeds capital N, we have the absolute value of gamma n. We'll break this into two parts. So the first part is, well, so the first part is we will go up to capital N terms. And the second part is we will take the rest of the terms. So this starts with the n plus 1th term, n plus 1th term, and goes up till the nth term, the little nth term. So that's what this is. We have broken it into two parts, and now we will use triangle inequality. This is less than equal to the first part, and the second part. All right. So now we will use that. Maybe let me write a strict inequality here. It doesn't make a difference, but it's just better for me. So now this guy we can estimate plus epsilon by 2a, absolute value of that. So what did we do? All we are saying is, okay, let me do one more step and then we will take care of. So again, triangle inequality gives me plus dot 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 this. So okay, this. So what did we do? We applied triangle inequality here. So this absolute value is dominated by the absolute value of the first term plus the absolute value of the second term, dot 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 the absolute value of this guy. And since product of absolute values is absolute value of product, we have this. So this is an estimate. This is not an equality. And now we can use this line to write. This is again an estimate. So each of these is less than equal to epsilon by 2a, or maybe strictly less than epsilon by 2a. So in the bracket we will have which in fact we can estimate by this summation. Let me write a k. Because these are some bunch of terms in this series. We have taken the whole series, so of course this dominates that because all of these are non-negative. So this is equal to because this is nothing but a, so this and that cancels out. So even though this is equal to, let me write less than equal to, it looks better. So what we have shown is therefore this is less than equal to this expression whenever little n exceeds capital N, or strictly exceeds. According to what I have done, this is strictly exceeds. Okay, so we have proven this, but this is a fixed number, and each of these, they go to 0 as n goes to infinity, because since this is convergent, we have ak goes to infinity as k goes to infinity. We saw this in the very beginning of our discussion on infinite series. So therefore this whole sum, since capital N is a fixed number, it does not depend on little n or anything. This goes to 0 as n goes to infinity. We see that this this thing for n large enough, this is less than epsilon by 2 plus epsilon by 2, which is equal to epsilon. Because you can make this arbitrarily small for large enough n, so you can make this smaller than epsilon by 2, and therefore for large enough n this is at most epsilon, and hence gamma n converges to 0, and we have proven the lemma. So it's a nice exercise. Right, so now we can go to the product. All right, so here is the hypothesis. We have two series, and we are assuming that the first one is absolutely convergent and the second one is just some convergent series. And under this much hypothesis, we will be able to define a sequence define a series which we will call the product series. And in fact, we don't need this hypothesis to define the series, but we want to prove something about the series that will require this hypothesis. So just given these two series, there is a natural definition of the product series, and that's as follows. We define the first term as just the product of, we define the zeroth term as the product of the zeroth term. So this indexing starts from 0, that's much more convenient. And then we define the first term as the product of the, in this fashion. So it's just the sum of the indices is 1. That's what C1 is. And where is all this coming from? So suppose I wanted to multiply without caring about convergence issues and whatnot. I had this expression, I just wanted to multiply. What would I do? I would multiply this with that, a0, b0. I multiply this with that, this with that, this with that, and this with everything, and that with everything. That's how I would multiply. So I would see a bunch of terms, and basically all of those terms, each term is of this form, ai, bj, where I and j are whole numbers, and we are just clumping them in a proper way. So this is the zeroth term, this is the first term, and similarly this is the second term where the sums of the indices is 2, and so on and so on. So we get the nth term is defined this way, sum of the indices is n, and this is how we form a new series. Now this is just a series, but under this hypothesis, this series is convergent, is the main point of the theorem. And moreover, the sum of this series is actually the product. So it works out the way it should. We want to just say that this is nothing but this sum with that sum, but here this is actually thought of as a number and this is thought of as a number. So, so I want to emphasize that. All right, so the sum of the product series is actually the product of the sums of the original series. So that's very nice, and let's see how to prove this. Okay, so we define the partial sums. Usually we write Sn, but here I'm writing An. This is the partial sum of the second guy. And let A be the limit of An, which is the sum of everything. So this is limit of An, which is nothing but this sum. And B is equal to limit of Bn's. Okay. Cn is defined as the partial sum of the product series. And what we want to show is if we define, okay, so define C as A times B, and here is what we want to show. This converges to A times B as n converges to infinity. So this will prove that the product series is convergent and it converges to the product of the sums of the original series. Okay. So we have Cn equals C0 plus C1 plus dot 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 Cn, that's what it is, which is A0 B0, that's C0. This is A0 B1 plus A1 B0 plus dot 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 A0 Bn plus up till, okay, let me write one more term. Okay, so that's what it is. And now we'll rearrange this in a nice fashion. So one can just verify that this is equal to A0 and this thing in the bracket plus and this story will go on for so this is just high school algebra, that thing is equal to this thing. Okay, but under our definitions or rather notations, this is which looks quite nice. And here is the thing. So define, so let beta n be the discrepancy of the partial sum with the sum. So that is the partial sum is the sum with the error. Beta n is kind of the error. So clearly this has to be highlighted. So one should note that beta n goes to 0. Simply because Bn converges to B as n goes to infinity. So this converges to 0. Alright. So therefore this is nothing but capital C, and so therefore Cn is A0 B plus beta n and this will go on for like that. And again, if we rearrange, we will find that this guy is equal to this plus something which we saw in the previous lemma. That's the kind of expression we saw in the previous lemma. Let me write one more term. All right, so this is nothing but that guy. And let me write gamma n. So gamma n is just this much has been written as gamma n. And since we have this hypothesis, or rather not hypothesis, but since we have this conclusion, and we already know by hypothesis that this is absolutely convergent, we know that this converges to 0. That's the previous lemma. So in this expression, this converges to 0, and what does this converge to? This converges to capital A. So therefore, Cn converges to AB plus 0 as n goes to infinity, and this is all that we wanted to show. So that proves our product result. So that's very nice. And this proof and all this notation, this very nice presentation I've taken from Sterling Barbarian. So this book, I think it's page 191 where this is given. So that's very well presented, this the proof of this result. And this whole presentation I've taken from that. Okay. So this is all that I wanted to say. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.